So welcome to this third day of the workshop on neutrons and dark matter. So we're super happy to have André Lessa here. So please, André, so you have 30 minutes, so 25 plus 5. I will let you know 5 minutes before the end.
Okay.
Thanks.
Right. Thanks a lot for the invitation. Wouldn't be my first time in São Paulo, as some other people, but still, it was very nice to be invited. I think we had some really nice talks so far. So I'm going to switch topics a little bit, not too much, but my focus will be more on the collider side of dark matter. And okay, so I'll start with this super beaten down diagram that we typically use to illustrate how all these different experiments have a role in searching for dark matter. And it can be quite misleading, I think, sometimes, because the complementarity of these different searches is very, very model dependent. Right? So what I'd like to discuss a little bit in my talk is really what's the role of colliders in this diagram when it's really competitive with direct and indirect detection, and when it can be the major player in searching for dark matter. Right? So I'll use this super simplified scheme for dark matter models, but it encapsulates the main features of all most of the relevant models. So I assume dark matter is coupled to the standard model through a mediator. The coupling between dark matter and the mediator is, I use lambda throughout this talk, and the mediator couples to the standard model through some coupling G, which can be a gauge coupling or some you call coupling or something else. And the mediator could even be standard model particles at this point, right? And we know that if the product of these couplings is order 1 or not too small, we can easily implement the freeze out mechanism, and we have mostly WIMPs, right, which require this dark matter mass to be GV or TV. And in this case, the direct detection is a perfect place for looking for or for searching for dark matter, since it's typically this scattering cross-section is roughly controlled by the product of these two couplings. We can also look for dark matter in colliders, and there, in this simplified framework, there are basically two main channels, an S channel and a T channel. So in the S channel, we basically pair produce dark matter, and we rely on initial state radiation to see these events, to trigger these events, and the main channel is MET plus jets, right? Or we could also have something radiating from the mediator, for instance, and we could have photons or Z's plus missing energy. The issue with this type of searches is that typically there is a huge background, right? Z plus jets, with Z decaying to neutrinos, or other vector bosons plus jets. So it typically requires the signal to be quite strong, right? These couplings have to be quite sizable, and the dark matter mass usually cannot be too heavy. Right? So within this WIMP framework, I will quickly illustrate some examples. So one typical simplified model, or even a full model, can be built implementing a U1 symmetry. So we have a Z prime that is the mediator, and it decays into two dark matter particles. Right? So one way to produce dark matter in colliders would be through this diagram. But of course, if this mediator couples to quarks, it also decays to quarks. So we can look for dark matter production as well as resonances, right? So this is something that was not done initially, but now the dark matter searches really look at these two possibilities. And here is a nice plot from Atlas with a combination of all sorts of constraints for this model. So this is the dark matter mass, and they plot against the in-spin-independent dark matter nucleon cross-section to compare with direct detection searches. And we see that Xeno and Panda are here, dark side are here, and all the searches from this, for all this, the constraints from the searches of resonances or MAT are this yellow region here. These are really searches for dark matter plus jets. And here are resonances, depending on how this Z prime decays, right? So if decays to TT bar, BB, or light jets. So these are the constraints. Everything above these curves is excluded by these collider searches. And we see in this diagram that typically the direct searches are much stronger in most of parameter space. Colliders really make a difference in this low mass region. It's not super low, but it's GeV-ish. Right? Another possibility where you don't have necessarily this resonance is if you have a T-channel mediator. And here is a recent study for the constraints on this model. There is a lot of information here, but what I want to point out is that direct detection and the relic abundance constraints all this region here. And what's left for the colliders to exclude is this region in parameter space here under this orange curve. Right? So the main point I want to make here is that these minimal models, they are highly constrained, typically by direct detection first and colliders second. So the direct detection searches are typically stronger for looking for these models. The collider searches or LHC constraints can also be competitive, but in some corners of parameter space. It's not, in most cases, not the main player for testing these scenarios. But of course, we can ask, we saw several examples throughout the workshop, what happens if these couplings are very small, right? So in particular, if the product of these couplings is very small. In this case, very roughly, direct detection cannot test these scenarios because this cross-section will be super suppressed. Of course, there are exceptions like resonance scattering, a very light mediator, and so on. But in most cases, direct detection cannot test this type of scenario. What about collider searches? So there are two possibilities. One is, okay, both couplings are super small and really, really small. And then there is very little hope of seeing it anywhere. And it'd be the most depressing picture, maybe, except maybe for Nicolas, who was very happy yesterday talking about gravitational freezing. Right? But I think for most people, it'd be the worst picture. Right? But if the coupling between dark matter and the mediator is very small, but the mediator has sizable couplings to the standard model, there is real hope of seeing or testing this scenario in colliders. Right? And we saw examples of this in several talks in the workshop, like Camilo's talk and Laura's talk. So I want to discuss a little bit further this type of scenarios and what we can, how we can use colliders to really test them here. So I use a very, very minimal scenario, but it's still very helpful because it has all the main features that we expect in these types of models. So we investigated it a year ago or so. So the mediator, I assume it's a vector-like fermion, and dark matter is a singlet scalar. There is a flipped-spin version of this model where the mediator is a scalar and dark matter is a fermion, which was also discussed by Laura and collaborators in this paper. So the Lagrangian is very simple. It's basically dark matter. This vector-like fermion can have a standard, or will have standard model quantum numbers. So it will basically couple to gauge bosons. And there will be a Yukawa coupling between the scalar, this vector-like fermion, and a right-handed standard model fermion, which can be a lepton or a quark. And then there are several possibilities for producing dark matter in the early universe and in colliders. Right? We have production through decays of this mediator, a T-channel-like production of dark matter, and associated production of dark matter and this mediator. The letters are switched here. So what about production in the early universe? How can we get the right relic abundance in this scenario? I stole this plot from Laura's paper because it's a very nice plot. And here it's for a specific model, but it shows, again, the main features in these small couplings models. So we have basically, this is the relic abundance versus this coupling here, lambda. The masses are fixed, and this, in particular, this plot is for a somewhat compressed scenario, but that's not relevant for what I want to show. So for very high or large couplings, we have the freeze-out, typical freeze-out mechanism, and here we would be in the WIMP scenario. If we go to slightly smaller couplings, basically the dark matter relic abundance is controlled by this mediator annihilation process. As we go to even smaller sizes of the coupling, then we enter this conversion-driven freeze-out, where one of the main players is this co-annihilation and conversion rate between dark matter and the mediator. And finally, for very small couplings, we have the freezing, which can be through scatterings or decays of this mediator. So the point here is that we can get the right relic abundance for basically all sizes of this coupling. Here it shows just a couple points where this curve crosses the right relic abundance, but this is for fixed mass of the mediator in the dark matter. If I play with these two extra parameters, I can bring these curves down. And so basically I can get the right relic abundance for a huge range of values for this coupling lambda. And this means that for this mediator lifetime, it can also go from prompt decays to really, really long-lived decays, right? So all this region here could be tested by these prompt searches where this mediator F decays promptly, and it also be tested by direct detection experiments, for instance. Once we go to smaller couplings, then the typical models can no longer be tested by direct detection, and what's left is this searches for long-lived particles at colliders. Right? So I'll focus the rest of my talk on this region of parameter space where colliders can really make a huge difference. So there's a huge program, and it has been growing a lot in the past few years for searching for these long-lived particles. There are all kinds of signatures. So going from a particle that's really stable and cross the detector all the way, and in the case outside, to particles that decay inside into displaced leptons or photons, displaced jets, and so on. The huge advantage of these searches is the background is really, really small. So it's very different from the typical dark matter searches using MET and jets, where there's a huge background. Here, the background is, in most cases, almost zero. So it can be sensitive to very small cross-sections for this mediator production. But it strongly depends on how the mediator is being produced and how it's decaying. Another point is that most of these searches are not strongly biased by dark model motivated scenarios. So there is still a lot of RPV SUSY and compressed SUSY scenarios, but it's not, many models do not really look into dark matter motivated scenarios. And I think this is something that's changing, but it's still a barrier we have to break. And so let me start discussing this in this minimal scenario, the minimal FIMP scenario, where I'm really at the super small couplings, right? So the couplings are order of 10 to the minus 10, or something of this order of magnitude. And the dark matter mass also has to be very, very small compared to this mediator. And the mediator here could be lepton-like or quark-like. So this production cross-section at colliders could be hadronic or leptonic. It depends. But the point is that in order to get the right relic abundance, this coupling, as I already said, has to be very small, which means the lifetime of this mediator is typically very, very large. And so if we consider the lowest dark matter mass allowed by Lyman alpha constraints, we get at lifetimes which are of the order of 1 meter, and then it goes up and up and up. So this is not super exciting at colliders because basically we just see a stable mediator. It would be hard to make a connection to dark matter. It could be anything. It doesn't have to have any connection with dark matter whatsoever. But in any case, we can still see what sort of constraints we get. So here I'm just for illustration, I'm showing this leptonic model. We've also studied the hadronic case. So this mediator is lepton-like, so it decays to dark matter and an electron or a muon. And then there are several possibilities, right? If it really goes all the way and decays outside the detector, since this mediator has electric charge, it will look like a heavy muon. And this is very easy to see. If it decays into inside the detector, so depending on the lifetime, it's the case somewhat inside the tracker, and this lepton is missed. This is going to be a hard lepton, but if it's missed, then this will look like a disappearing track, right? A track that goes all the way here and then suddenly disappears. And also, another possibility is if this lepton is reconstructed, then we have a displaced lepton. But there are some issues with the searches that look for these signatures. One is, of course, there is a hard cut on this displaced lepton here, or on the disappearing track. We really need to miss this lepton, which in this model is not so easy because this will be a hard lepton. And in this search, at least at this point, the search also required that in the search for displaced leptons, it requires both a muon and an electron in an event. So would have this mediator, it would have to couple to both muons and electrons. One branch should have to decay to an electron and one to a muon. Right? So the searches, the constraints are here. These are on the mediator mass versus lifetime. So most of the parameter space, right? So it should be above this dashed line here. So most of the barometer space is really excluded by HSCPs, this heavy stable charged particle searches. Then there is some small corner here that can be tested by this disappearing track, but under this assumption that this lepton is really missed, which is not a given here. And then in this region, which is not really well motivated, we could test this scenario with the displaced leptons. Right? But one of the points here is that these searches were not intended to test this specific scenario. They consider completely different scenarios, so they are not optimal. Right? There are a whole bunch of things that could be improved and could really increase the sensitivity to these FIMP-like scenarios. Another possibility is, what if these couplings are not so small? They're small, but not super small. Then if the couplings are of the order of 10 to the minus 6, there is another possibility, which I had mentioned before, which is this conversion-driven freeze-out mechanism. It requires the mediator and the dark matter masses to be somewhat compressed. And we could still use the same process to search for it at colliders. So the main difference here is that this mass difference here is small, and since the coupling is not so small, the mediator can really decay inside the collider. Has a higher probability for it decaying inside the collider. So here is a plot for in the dark matter mass versus compression plane. There's a lot of information here. I'll just guide your eye to the main points. So one point is that lifetime goes in this direction, and it's given by these dotted gray lines. So here the mediator lifetime is of order 2.5 centimeters, 5 centimeters, and so on. So it's really inside the tracker. Everything under this solid dark line is consistent with the relic abundance. So the other parameters are adjusted to fit the correct relic abundance. And then we have the collider constraints here. So there are match searches that apply really for the cases where this F decays promptly. So here it has high probability of prompt decays. Here there are smaller probabilities, but still it can be searched. It can be tested with these searches. Then we have all the displaced searches, right? So for instance, here's the disappearing track search. Here is the HSCP search. And here is a search that looks for jets coming from displaced vertex. And the point is, again, all these searches were not intended for this type of model. And there are all sorts of choices made in the event selection that really reduce the efficiency for testing these scenarios. So for instance, if we modify a little bit this search, we could go from this exclusion curve to this dashed line here. Right? But since the search was not intended for this scenario, its potential is not fully exploited here. So this is mostly to illustrate that these collider searches for long-lived particles have a huge potential. But on the other hand, there is still not a lot of talk between the dark matter community and the collider community. So there has been this effort to integrate more these communities, as well as the phenomenological community and the experimentalists. So we have a workshop twice a year for these LLP groups. And there is also a reinterpretation forum that discusses how we can really apply these searches to other scenarios. And unfortunately, there's not a tool that can really be applied for testing dark matter models using these long-lived searches, but there's a lot of work under development here. I can talk about it later in the discussion if someone wants to know more about it. There's also a recasting repository with codes for testing these scenarios for analysis. So the idea here is whoever has gone through the trouble of reinterpreting these models can put their code there and be useful for other people who are starting on it. So a last thing I want to mention is that the long-lived scenario has also a very nice feature. It's a somewhat bold proposal here. This would have to be done at the high Lumi LHC. But the idea is that in this minimal scenario, we could really test or measure all the couplings if we see a signal. So for instance, measuring this cross-section would allow us to determine this coupling G. Since I can, if my mediator decays inside the tracker, I can reconstruct its momentum and I can infer its mass. Looking at the decays, I can also reconstruct the dark matter momentum and then get the dark matter mass. And finally, looking at the decay position, I can try to reconstruct the width and then reconstruct this coupling lambda. So this is a scenario where we could really, it would be possible to measure all these couplings and test the compatibility with the relic abundance. Right? So this is really minimal scenario, that's why it's possible, but because the particle is long-lived, we have more information than in prompt decays. So we can really measure these couplings way better than in the WIMP scenario, for instance. And then we could, in principle, measure the relic abundance if we take this model seriously. So, okay, just
Sorry,
in
André, I
time.
forgot to tell you that you have exactly perfect.
Yeah, okay, I think I'm almost done, right in time, I guess. So just to my conclusions, from what I try to argue here is that for WIMP models, LHC is relevant in some corners, but it's not the main player. In these Fibly couple models, which doesn't necessarily have to be FIMPs, could be this other example, for instance, where we have small couplings, but not too small. The LHC could indeed be the main player for searching for dark matter. And there are other scenarios also that I have not discussed, like modified cosmology or early history, and highly compressed scenarios, and so on. So I think one important point is that these long-lived searches on the collider side are still not strongly connected to these dark matter models. This is something recent, has been happening in the last year or 2 years. And I think it's very important to make this connection stronger. So new ideas are always welcome from the dark matter community. And whoever is interested, there are also these LLP workshops where all these topics are openly discussed. Okay, so that's what I had to say. Thank you.
Excellent. It's André. Thanks for. Are there questions or comments? Laura, I can see.
Yes, thanks. Thank you for the talk. It was very nice, André. And I just have a question about the last thing you mentioned. I mean, I know only one paper that was discussing the fact that you could reconstruct everything, but it seemed to be still something a bit. I mean, like something that could happen in heaven somehow. So I mean, what you are working on this? I mean, what is your I mean, your opinion like that on that?
Yeah, it's okay. So yeah, there are some papers that show, there is actually one paper, I think, that shows that you can reconstruct the masses.
Yes.
Fairly well. The width is way harder to reconstruct because, of course, you have decays, you have a distribution of decays, and it's harder to fit and get this width correctly. But yeah, we are working on it, but we don't have results. And I think this really has to be considered for the high luminosity LHC. It's not something that we'll do in the next run. We really need a lot of data. And yeah, so yeah, it's something we are working on, but we don't have results yet. The masses seem okay, and the cross section is also fairly easy to reconstruct. The main issue really is the reconstructing the width.
But when you say fairly easy, I mean, it's like tomorrow you see a signal, you can I mean,
no.
Okay.
No, you need, of course, no, you need, yeah, I would say that it's possible maybe by the end of run 3 or so, if we see a signal right away.
Okay.
So
thanks.
I would say that, yeah, this is more long term. Yeah, not right now. Yeah.
Thank you.
Sure.
Thanks. Maybe a last question. Something in the chat. Yes, Sarah, please.
Hello. I want to know how can we fix all of the coupling. We have a coupling for Z prime to fermions. We have a coupling Z prime to dark matter. We don't know about the mass of Z prime, and we don't know about the mass of dark matter. How can we fix them?
Okay, so how can we fix them? How can we measure them, or fix them from the theory side? For me, that was not clear.
Fix them for the theory side.
I mean, yeah, in this simplified scenarios, you can you do have freedom to choose these couplings with some ranges, of course. Typically, you do have, if you're fully general, you have couplings to all generations and quarks and leptons if you're thinking about Z prime. So you do have a lot of freedom. Some of the parameters are fixed just by requiring the relic abundance. And then you have all the constraints that will push these masses to somewhat higher values like TeV-ish. But it cannot be fully fixed from the theoretical side if you're really considering just the minimal model to explain dark matter. And so the main constraint you have is the relic abundance that will fix one of these parameters, but not all of them. Yeah. So in the planes, I showed, I think, when I showed the constraints for the Z prime from Atlas, they do have, basically, if you see here in the lower corner, they did fix a whole bunch of parameters. Right? For a specific choice of parameters. Then there is the dark matter mass, and the Z prime mass is fixed by the relic abundance in this plane. So yeah, there is a lot of freedom here for sure. I don't know if that answers your question.
Okay, thanks, André. I see a couple of questions more from, for example, Roberto, but I propose to let all these other questions to the discussion session that will take place at the end. So let's thank André once again. And the next speaker is Miguel Escudero. So Miguel, are you there?
Yeah. Let me share my screen. Got it. Can you see my screen, guys?
Yes, perfect. You can make full screen. Yes.
Awesome. Yeah, so thank you very much for the invitation. It's a pity we cannot be all of us in Brazil, but the physics is very good regardless of where we are. So thank you for that. So what I'm going to discuss in this talk is a new mechanism for baryogenesis and dark matter from the CP violetin oscillations and subsequent decays of B-mesons in the early universe that we have very recently named B-Mesogenesis. Let's see how the name goes. So the mechanism is based upon this reference with Gilliel and Nelson, as you can see there. And at the moment, we are working actively on an update regarding the collider signal. So I'm going again in the same trend that André initiated this morning. That we expect this is with Gonzalo Alonso Alvarez too, here shown. And we expect it to have it early January. We will see. This one is coming. So let me jump straight to the mechanism. But actually, before, I think it's good to revisit what we know and what we don't know about the universe. So this is the picture that we all know very well. 5% of it corresponds to baryogenetic matter, 26% of it corresponds to dark matter. That's why we are all talking and discussing. And 69% of it corresponds to dark energy. And we have actually measured very well each of these three components. The pertinent question is, well, how much of this chart pie do we actually understand? Or to put it in another way, what fraction of the energy density of the universe comes from physics beyond the standard model? And the answer to that question is 99.85%. If it were for the standard model, we should be living in a universe dominated by radiation with just photons and neutrinos. So our aim with the mechanism was to give us, potentially give us an understanding of why are we living in a universe with only matter and not antimatter, and what is the origin and nature of that matter. So the main features of the mechanism that we developed more than 2 years ago is that in this scenario, baryogenesis and dark matter are linked. The baryon asymmetry in this setup is directly related to B-meson observables. It's because of this fact that if the mechanism is applied in the universe, it will lead to unique collider signatures. And as a result of these unique collider signatures, we expect the mechanism to be fully testable given the reach of current collider experiment. So this is the outline of the talk. First, I'm going to discuss what are the key ingredients of the mechanism of B-Mesogenesis. Then I will highlight it with a minimal model and discuss briefly the cosmology. And then I will move into what I think is the most interesting bit, which is what are the implications for collider experiments, and also, of course, discuss the dark matter phenomenology. And then I will just summarize and conclude. So already in 1967, Sakharov outlined what are the three necessary conditions in order to generate the universe we observe, namely a universe with matter and not antimatter. So for that, we need to violate C and CP. And the reason is simple. We need to produce more particles than antiparticles. And for that, we need to violate both C and CP. In addition, we need to be out of thermal equilibrium, because in thermal equilibrium, the rate of producing particles and antiparticles is the very same one, regardless of whether C and CP are violated. So we need to be out of thermal equilibrium so that the rate of producing particles is larger than the rate of producing antiparticles. And finally, if the asymmetry we want to generate is of particles against antiparticles, and these particles have a baryon number needs to be violated. So how do we address each of these conditions? So the first one, and here's where the main novelty of the mechanism comes in, and this was a key idea of Van Nelson, was, well, let's put into use a naturally occurring CP violating system in the standard model, which is the neutral B-Meson system. So the key quantity that measures the CP violation in the neutral B-Meson system is the semi-leptonic asymmetry, this ASL, that I'm going to refer through the talk extensively, and is defined as the imaginary part between the ratio of the width mixing and the mass mixing in the B-Meson system. And so that's the definition in terms of mixing parameters, but in terms of things we can measure is literally the number of times a B-Meson will decay into matter minus the number of times a B-Meson will decay into antimatter divided by the sum of the two. So it's very clear that if this number is different from 0, then CP is not a good symmetry. We know the electroweak interactions violate CP, and these numbers are different from 0 in the standard model, and these are the values for the B sub D and B sub S mesons. So they are at the level of 10 to the minus 5 and 10 to the minus 4. And they are small because the only difference between these two quantities is the absence here of a top quark loop, and due to this ratio, they are at this level, but they could have been larger depending upon the top quark mass. These should be compared with current measurements, and these are the current world averages. And you can see that the current uncertainties are at the per mil level, and that error bars are compatible with no CP violation. You can see that the error bars are such that they are a factor of 4 and 100 larger than the standard model predictions. So these are the numbers in the standard model, but then beyond the standard model, there are many scenarios that can enlarge these asymmetries from the standard model value to values around 10 to the minus 3. And this includes supersymmetry, extra dimensions, leptoquarks, C-prime models. There is an array of models that can enlarge these asymmetries. So that was the first Sakharov condition, and now the second, out of thermal equilibrium. And also, we need to address how do we produce B-mesons in the early universe, because we want to use them for baryogenesis and dark matter production. So the way we achieved that was by requiring the presence of an out of equilibrium particle that is dominating the energy density of the universe and decays, and reheats it to a temperature of around 10, 20 MeV. For that to happen, the particle should be very, very weakly coupled and should have a lifetime of around a millisecond. These reheating temperatures may seem low, and they are low, but they are totally fine regarding observations, provided that the reheating temperature is larger than 5 MeV. For temperatures above that, we don't spoil BBM predictions or CMB observations. So what are the properties of this out of equilibrium decaying particle? Well, if it's a scalar particle with a mass above the B quark threshold and below the electroweak boson mass, it will generically decay into B quarks. So we have the right properties for this particle to produce B quarks in the early universe. Since we are talking about temperatures that are below the QCD phase transition, then indeed these B quarks will hadronize, so they will produce B mesons. One important detail is that these B mesons are going to be produced in the early universe, but they are not produced in vacuum. The early universe is not like a collider. So in the early universe, there is a hot dense plasma, and in particular there are electrons. And even though the B meson is a neutral and spinless system, it's made out of quarks that have a charge, and therefore electrons and B-mesons can interact. And it's completely dangerous if we want to use the CP violating oscillations of B-mesons to generate baryogenesis, because these interactions could decohere the oscillations. But we explicitly check that that doesn't happen for temperatures below 20, 30 MeV. That's why we need to live in this 20 MeV temperature region. The third Sakharov condition is baryon number violation, and here I put a question mark, and the reason I did that is because in our scenario, baryon number is actually conserved. And this is in a similar fashion to halogenesis by Tulin and collaborators. So how do we actually make baryogenesis if we don't violate baryon number? Well, the trick is to make dark matter an anti-baryon and generate an asymmetry between the visible and the dark sector, thanks to the CP violating oscillations and subsequent decays of B-mesons. So due to the CP violation in the oscillations of the B-mesons and their decay into visible baryon and dark sector states, we can end up with a situation like this. So baryons in the visible sector and anti-baryons in the dark sector, so that the total baryon number of the universe is 0. But yet baryogenesis and dark matter production are achieved. Very importantly, for this to happen, we require a new decay mode of B-mesons into dark matter, which will be missing energy in the detector, and a visible baryon. So this is a summary of B-mesogenesis. So we have an out of equilibrium late time decaying particle, this capital phi. It decays, it reaches the universe at temperatures of around 15 MeV, and it decays into big quarks. These big quarks quickly hadronize and produce B-mesons. The neutral component of these B-mesons will undergo CP violating oscillations and will subsequently decay into visible baryons and dark sector anti-baryons. And this will allow to generate baryons in the visible sector, so successful baryogenesis, and dark matter, which will be a dark sector. As promised in the introduction, in this setup, the baryon asymmetry is directly related to two observable collider experiments. One of them is the branching fraction of the new decay mode of a B-meson into a dark sector anti-baryon, which will be missing energy in the detector, plus a baryon, plus any number of light mesons that could be produced in the decay. And it's also proportional to the CP asymmetries in neutral B-meson decays. So it's directly related to two things that we can actually measure, or potentially colliders, as I will discuss momentarily. So we need to address how a B-meson can have a non-standard decay, and here things get a little bit more technical, and the slide is a little bit too much, but I'm going to discuss it step by step. So we want a decay like this to happen. We want a B-meson to decay into a visible baryon plus dark sector state. And for that, we need a new color mediator. We need a new mediator that triggers this decay. It has to be a boson. And for that, we chose a color triplet scalar that we call it Y, and it has these quantum numbers, and it has this type of interaction. So it couples to a U quark, a B quark, and then it couples to an S quark, and also to this psi. Psi being a Dirac dark sector anti-baryon. Now, this cannot be the entirety of the dark sector, because this particle effectively couples to 3 quarks and will eventually decay. So you need to add more species to the dark sector, and the two that we chose were a scalar anti-baryon, that is a standard model singlet, this phi, and a standard model singlet, Majorana fermion, psi. Yes. So these are the particles that will actually compose the dark matter that we observe if the mechanism is at play in the early universe. And we know kind of very well where the masses should be. We know that the masses should be above 1.2 GeVs. That's more or less the chemical potential of a neutron in a neutron star. So it needs to be above that, because this particle carries baryon number. And we know it has to come from the decay of a B-meson, so it cannot be too heavy. So it has to be below roughly 2.5 GeV. So we have a very clear window of what the masses of these particles are. Finally, of course, we want to explicitly see that the decay can happen. So then you need to plug in these numbers and get what a branching fraction this could lead to of a B-meson decaying into dark matter, a visible baryon, and any number of pions. And you see that values of the Fermi level are achieved when the mass of the triplet scalar is around 2 TeVs with couplings that are ordered electroweak. And we know that the mass of this particle due to force jet searches and square searches should be above 1.2 TeVs. So you see that a large branching fraction could be potentially achieved. So with this, I move into the cosmology. I'm not going to discuss in detail the Boltzmann equation. I'm just going to flash them. We need to solve for the expansion of the universe, the decay of this out-of-equilibrium particle, how the universe reheats. We need to track the dark matter evolution, so how the Xi and the phi and the anti-phi evolve as a function of temperature over time. And we also need to track the baryon asymmetry. Something that is particularly easy is that in this scenario, baryon number is conserved. So the baryon asymmetry is directly the number of anti-baryons in the dark sector minus the number of baryons in the dark sector. And again, doing the math, you can easily show that indeed the baryon asymmetry is directly related to the CP violation in the neutral B-Meson system and to the branching fraction of this new decay mode. And of course, one needs to take into account the coherence in the early universe because it can be relevant and we did take it into account. I'm not going to discuss them further, but if there are questions, please ask me later. So I'm going to jump straight to the solutions in terms of the relevant parameter space that I'm highlighting here. So on the y-axis, I chose minus the semi-leptonic asymmetry in the B sub D meson, and in the x-axis, the semi-leptonic asymmetry in the B sub S meson. So they characterize CP violation in the B meson system. This orange contour corresponds to current world averages, and this corresponds to the standard model predictions. And here I have superimposed the result of a full parameter space exploration that shows that in all these red region of parameter space, one can achieve baryogenesis and dark matter production within our mechanism. So one of the conclusions you can reach from seeing this plot is that the measured semi-leptonic asymmetries imply that the branching fraction for this new decay mode should be larger than 10 to the minus 4, so rather large. And then also, we don't only have access to measurements, direct measurements of these quantities, but we can also take all the relevant CP violating data in the neutral B-Meson system, which are not only these two quantities, and one can perform a global fit to have an indirect test of how large these quantities can be. And this is what is highlighted here in gray, is a global fit by UTFit that shows that given all global data on the oscillations of CP violation of B-mesons, the branching fraction should be larger than 1 per mil. You may have seen that there is overlapping parameter space between our predictions and the standard model prediction of these asymmetries, and that's correct. In this region of parameter space, one can obtain baryogenesis given the standard model CP violation in the neutral B-Meson system. Of course, that is corresponding to a branching fraction that is 10%, between 2 and 10%, which is kind of a large number. And I will come back to that in a minute. So at the moment, that's allowed by data, but it may not be. Soon we will see. So, I've been talking about this new decay mode, and you may be wondering, well, but we know the B-Meson system very well, right? For example, B factories have a sensitivity at the level of 10 to the minus 5 for branching fractions that have missing energy in the final state, like B to K nu. And then when there is no missing energy in the final state, like B to mu mu, the sensitivity is at the level of 10 to the minus 10. So we really know the B-Meson system really, really well. So what are the constraints on our mode? Well, at present, there are no current constraints on these decays because the decays have not been targeted. There is no published result on a search that targets a B-Meson decaying into a missing energy. In our case, is an anti-baryon in the dark sector and a visible baryon. So we don't have that kind of precision yet. The best we could do was to look at the total width of B-Mesons, and we have seen that there is a measurement of the inclusive decay of B-Mesons into protons and antiprotons that is at the level of 8%, and these can turn into a constraint of roughly 10% on our branching fraction. So at present, this is the best limit you can place because there are no dedicated searches. So baryogenesis requires this branching fraction to be larger than 10 to the minus 4. And B factories have a sensitivity at the level of 10 to the minus 5 for processes involving missing energy. So we could expect a similar sensitivity for this type of processes. In fact, we are in contact with experimentalists, and there are ongoing searches with Babar, Bell, and Bell2 data on our decay modes. So given the reach, we actually expect the mechanism to be fully testable just by looking at these new decay modes. So that was the, let's say, baryogenesis / collider phenomenology section, and now I'm going to turn into the dark matter phenomenology, which is the topic of the workshop. And this is more or less a picture of how the dark sector, the dark matter, would look like within our scenario. So you can see it's partially asymmetric, and the reason is that this particle carries baryon number 1. And for only antibaryons to make up the dark matter, they should have a mass of 5.3 GeVs, and that cannot happen because then they cannot come from the decay of a B-meson. So we have a partially asymmetric dark sector because we have this constraint on the masses. But of course, in order to have a symmetric component in the dark sector, we need to deplete some of the number density, and then we perform a full parameter space scan and show that in order to obtain the observed dark matter abundance, the cross-section in the dark sector should be at least 1 order of magnitude larger than the WIMP for GeV scale masses, which is the ones that are relevant. The reason this is half order of magnitude larger is because our process is non-thermal, has nothing to do with typical WIMP freeze-out. We are producing dark matter particles, and then they need to annihilate in order to be depleted. So a pertinent question that one can ask is, well, what kind of dark sector allows you to have such large cross-sections, but at the same time being compatible with the very strong constraints coming from CMB observations on S-wave annihilating relics? So to highlight the point, here I'm showing the constraints on the annihilation cross-section as a function of the dark matter mass. Here, everything below these lines is, everything above these lines is excluded by Planck, and we live there. So what kind of dark sector allows us to actually live there? So what we did in the paper almost 2 years ago was to highlight 3 possibilities. So one of them is maybe dark matter annihilates into stellar neutrinos. Why this is a good possibility? Well, the annihilation can be predominantly P-wave, and then you don't have any signals at Planck because you only constrain S-wave annihilating relics with the CMB. The second possibility is to annihilate into active neutrinos, because the constraints on dark matter annihilating to active neutrinos are very mild, or maybe, let's say, milder. And this may connect with the next talk by Sergio. Essentially, I'm showing here the same parameter space as before, but now annihilation only into active neutrinos. Here on the y-axis is the annihilation cross-section, and this is the dark matter mass. And this is a plot that I took from this paper by Bell and collaborators. And here is where our mechanism will lie if the annihilation is into active neutrinos, and this is where current super K constraints lie. And these are projections for hyper K. So at present, this is totally fine regarding super K constraints, but hyper Kamiokande could have the potential to test such large annihilation cross-sections that occur in our mechanism. And finally, the third possibility that we highlighted was, well, maybe there are additional particles carrying baryon number in the dark sector. Why this could be relevant? Well, if dark matter is made of only anti-baryons, then there are no annihilations, and we don't have to care about Planck constraints. So we highlighted the point with a new scalar baryon we call A, with baryon number 1/3, but it has nothing to do with a quark, so it's a standard model singlet. And the good feature of this particle is that the asymmetry in the dark sector could be transferred to this state by just annihilations or semi-annihilations. And then we know that the ratio between the dark matter and the baryon energy density is around 5, which will mean that the mass of this particle will be 1.6 GeV. And I think this is a cool scenario because it could give us an understanding of why actually this ratio could be 5, and at the same time why you are not seeing any signals from indirect searches. Unfortunately, in the regard of... Yeah?
Sorry, you have something like 4 minutes.
Good, thank you. I will finish soon. So on the detection side, in the dark matter part, unfortunately, there are no direct detection signatures, and the reason is that there are no direct couplings between dark matter and light quarks. So we don't have a typical WIMP-like scattering signal. The dark matter particles could interact with lighter quarks via loops, and this is strongly suppressed. And one could imagine processes of this type. So a dark matter state comes in, interacts with a neutron, and then in the final state, you have a lighter dark sector state and mesons. This is a potential signature that would look like nucleon decay, but the problem is that when you compute the number, it's tiny and is unobservable. So that's unfortunate. It's hard to detect this dark matter. So to summarize, we develop a mechanism for baryogenesis and dark matter from the CP violating oscillations and subsequent decays of B-mesons in the early universe. That I think one of the main novelties of the mechanism is that it directly relates the CP violation in the CP violating system, which is the neutral B-meson system. It is a system that occurs already in the standard model, and it relates it to baryogenesis. In this setup, baryon numbers is conserved, and this allows us to make a direct connection between dark matter and baryogenesis. If this mechanism is at play in the universe, it will lead to distinctive experimental signatures. So it will lead to a positive semi-electronic asymmetry in the neutral B-meson decays with a value greater than 10 to the minus 5. And in this scenario, both neutral and charged B-mesons should decay into baryons and missing energy with a branching fraction that should be larger than 10 to the minus 4. There are ongoing searches for these processes at Babar, Bell, and Bell 2. And given the sensitivities of B factories to processes involving missing energy, we expect them to fully test the mechanism at current collider experiments. So just a few words for outlook. I think something interesting to consider would be, well, are the flavor anomalies in B2S transitions related to our positive semi-electronic asymmetry? Typically, leptoquarks and C-prime models induce mass mixing in the BS system. And this could easily lead to a different semi-electronic asymmetry. So maybe there is a connection. I think that would be interesting to explore. Are there other possibilities for the dark sector? I highlighted 3, but there, of course, could be more, and they could lead to a richer phenomenology. A pertinent question would be, well, what kind of UV theory allows you to have a heavy color triplet scalar at the TeV scale, but then particles that are the standard model singles at the GeV scale? And I think a nice example on that direction is a supersymmetry realization of the mechanism by Gonzalo, Gili, and Wang Xiao. And finally, regarding experiment, I think I'm really curious to know how well Babar, Bell, and Bell 2 would constrain, potentially measure this non-standard this branching fraction of the decay of a B-meson into dark matter plus a visible baryon. So I'm going to conclude by highlighting that our paper will appear soon, and in there we are exhaustively analyzing all the correlations of the signals that are present in the model. I think it's going to be a nice paper, and it will be out hopefully in early January. And that's all. Thank you very much for the invitation and for your attention.
Thank you very much, Miguel, for this nice talk. So are there questions or comments for Miguel?
Yes, I have a question maybe.
Sure.
So how do you avoid the constraints in direct detection in the B-bar channel?
Can you repeat again? Sorry.
Yes, in principle, the reverse process may be possible, and maybe there are constraints from indirect detection in the B-bar channel, or not?
No. So let's have a look at this. So in our scenario, this particle that is a Dirac fermion interacts with a quark and a particle with color. It's a triplet scalar, right? And then this particle interacts with 2 quarks, one of them being a B quark. But this particle doesn't make the dark matter. The dark matter is made out of these other 2 that do not directly interact with quarks. So there are, So yes, we need another annihilation channel, and this was highlighted here precisely. So Yes, so we live there, and if you annihilate into BB bar, you're screwed. If one of these states annihilates into BB bar with this cross section, the mechanism doesn't work, and then you need to do something, right? And I don't think it can be to BB bar because the masses are below the B quark threshold, right? You need a dark matter mass that is above 5 GeVs. But in any case, any other standard model final state that is not neutrinos will be spoiled if the annihilation is a wave. So the ways we put forward where maybe annihilation is P wave, I think that would be natural if you have stereo neutrinos. If these stereo neutrinos are heavy, you can annihilate directly into active neutrinos via mixing, and then the annihilations, the constraints there are mild. So you are fine, at least today. Maybe in 20 years, the thing changes. And the final possibility is maybe there are no annihilations because the dark sector is completely asymmetric, so there are no A stars to meet and annihilate with. I don't know if all that does that answer your question?
Yes, of course. And also maybe in the gamma channel, gamma rays channel, there are constraints or no?
Well, yeah, okay, true. So we didn't, I didn't consider them. So the gamma, well, here, right, that's the line from Rebecca Lane and collaborators. So yeah, if you annihilate directly into gamma rays with this annihilation cross section, then that doesn't happen. But again, the annihilation could be to neutrinos, it could be P wave, there may not be annihilation.
Okay, thanks, Miguel. So I can see another question from André, but maybe it's better if it's okay for you guys to let it for discussion session because we're kind of running a bit late. So thanks a lot, Miguel, and let's welcome now Sergio. Are you there, Sergio?
Hello. Shall I share my screen?
Yes, please.
Okay. I guess. Let me see. Okay. So do you see the screen?
Yes.
Okay. So thanks. First of all, yeah, thank you to the organizers, in particular to Nicolas Bernard for the nice invitation. As everyone has said, it's really a pity that we cannot be there in Sao Paulo, such a nice place, and I hope we'll make it next time. And today I'm going to tell you about new trends in dark matter, but also all trends in dark matter in the context of searching dark matter with neutrinos. And I will try to give a broad overview of how we can do so. So searching dark matter, searching for dark matter with neutrinos. But let me start by just saying a few words about the potential and generic neutrino dark matter connections. So, this is not working. Okay. So if we want to study neutrino properties, or we want to search for dark matter, the obvious way to do is just to use neutrino detectors or dark matter detectors. But of course, these two sectors could be connected, and one in principle can search for dark matter with neutrino detectors by trying to measure or detect neutrinos produced from dark matter, let's say annihilations or so. Or one can also use neutrino detectors to detect dark matter via dark matter interactions at the detector. These are like similar to direct detection detectors for dark matter, using neutrino detectors for that. But of course, one can also study neutrino properties using dark matter detectors, and these two sectors could be even more intimately connected by, for instance, neutrinos could be a good dark matter candidate, like KV neutrinos, or dark matter could play a very important role in neutrino mass generation. We heard a talk, well, probably more than one, but at least I remember Roberto Liner's talk on Monday on these. And these neutrino dark matter interactions could show up, for instance, in astrophysical and cosmological observables. Also, these neutrino dark matter interactions could affect the propagation of astrophysical neutrinos from the sources to us and modify the expected flux in many different ways. And so in this talk, I will not talk about everything. I will just concentrate on detecting, most part of the talk, on detecting dark matter with neutrino detectors using neutrinos. But I will also mention the effects of neutrino dark matter interactions on these astrophysical neutrino flux that are detected in neutrino detectors. And if I have time, I will just touch upon the effects on some astrophysical and cosmological observables. Okay, so let's start with how we search for these neutrino dark matter interactions. Basically, there are three types of signatures that one can expect. One is searching for a new signal, say on top of a known background, like for instance, searching for annihilations on top of the atmospheric neutrino background. Then we also can search for features on known spectra, like features on astrophysical flux of neutrinos that encounter some dark matter in the wave from the source to the Earth, and then those interactions could modify the spectrum, for instance, producing a dip in the spectrum. And finally, we can also search for these neutrino dark matter interactions by cosmological or astrophysical observables, because these interactions produce a damping on the matter power spectrum, suppressing the power at the smaller scales. As I said, I will not talk much about this, maybe just at the very end, and I will focus on these two things, which is detecting, searching for dark matter with neutrinos and neutrino detectors. Okay, so what are the sources of neutrinos that we have? So we have natural sources, and we have man-made sources. So just from order of from distance, so the closer to the farthest away sources, so we have atmospheric neutrinos. We have neutrinos from the radioactivity of the Earth. We have solar neutrinos, supernova neutrinos in the MeV range. We have also very high energy astrophysical neutrinos, and then we have cosmic relics, the cosmic neutrino background, the analogous to the cosmic microwave background. And then we also have man-made sources like those neutrinos, nuclear reactors or particle accelerators. And then, of course, we might have exotics like the neutrinos produced from dark matter annihilations or decays. Okay, so let us start with searching for dark matter with neutrinos using searching for a new signal on top of a background, which in basically all the cases I will be considering in the next slides is the atmospheric neutrino background. So basically there are two targets, two generic targets that one can consider. On one hand, we have the annihilations of captured dark matter in the sun or the Earth. In this case, this is sensitive to the scattering cross-section, so this is complementary to direct searches, and only valid for masses about a few GeV. Then we have also annihilations or decays in halos, like for instance, annihilations or decays from dark matter in the galactic center or dwarf galaxies, etc. This is sensitive to the annihilation cross-section, and it could be linked to the thermal production in the early universe. Then if we are searching for signals from decays, this is sensitive to the lifetime of the dark matter. That should be longer than the age of the universe. So, as I said, we are in the next slides. I will be talking about these dark matter annihilations or decays from these two different type of objects, so let's say. Okay, let's start with dark matter capture in the sun or the Earth. So the idea is the following, and dates back from the mid-80s. And the idea is that we have local galactic dark matter particles that are floating around us, and eventually they could elastically scatter with the nuclei of the sun and get to a velocity which is smaller than the escape velocity of the sun, so they get gravitationally bound to the sun. And after many orbits, many interactions with the nuclei of the sun, they can actually get trapped within the sun, and then after additional scatterings, that would give rise to an isothermal distribution. As I said, this was proposed in the mid-80s and by Professor Spergel, and actually soon after that there were more detailed calculations of the capture rate, the evaporation rate, and all the details of this calculation that I won't have time to enter today. So these dark matter particles that are trapped in the sun can can and hopefully do annihilate into standard model particles. And after some time, this annihilation rate and the capture rates typically equilibrate in an object like the sun. This is not so in the Earth, but I will not be discussing much about the Earth today. I will show you basically all results are for the sun. And if equilibration takes place, basically what happens is that the annihilation rate is proportional to the capture rate, and the capture rate is proportional to the scattering cross-section, and this is why these searches are complementary to the direct detection searches of dark matter. Both are dependent on the scattering cross-section. And what makes neutrinos unique in this type of searches is that among all the standard model particles that could be produced in the interior of the sun from dark matter annihilations, only neutrinos can escape and actually be detected at detectors. So, and this was soon realized after the proposal of this idea. Okay, so what are the limits we have from the sun from different experiments? We have superkamikande, we have IceCube, Antares, also Baikal and Baksan. Baikal and Baksan could also give some limits. But in general, I won't get into much details, but here we can put limits on the spin-independent cross-section or the spin-dependent cross-section. And typically for high masses, neutrino detectors, neutrino telescopes dominate, let's say about 100 GeV or so. And the different lines here are annihilation to different channels, and different colors are different experiments here. At low masses, a detector like Super K set more stringent bound, but in any case, as you see here, these are the bounds coming from direct searches, and they are several orders of magnitude more stringent than those coming from neutrinos from the sun. And this is what happens in the case of spin-independent cross-section. This is different from what happens in the spin-dependent, for which the limits coming from direct searches are much weaker. And in this case, the limits coming from the sun can be the most stringent ones. Then we have also other type of detectors like INO, which is a magnetized iron calorimeter proposed in India, Dium, Kamlan. Also, I want to show you here the prospects for IceCube in the future upgrade, and that would improve these limits by 1 or 2 orders of magnitude, just because of the size is so much larger. Okay, but usually when we talk about these limits, we are talking about neutrinos with energies close to the fraction of the dark matter mass. So, and we usually we only consider annihilations into heavy quarks, gauge bosons, or tau leptons. So what about annihilations into light quarks, muon, or even electrons? Why they are not usually considered? And the reason is that, well, electrons and positons do not produce neutrinos, so that's it. And muons and light quark hadrons, and therefore mesons like pions and kaons, lose energy very fast. So they basically, when they decay, they do it at rest. So they produce a flux of MeV neutrinos, but those MeV neutrinos can be searched for. And actually, this is what was proposed in these 2 papers already. This was finished in 2012, so 8 years ago, by these 2 groups, myself and Nicolas Bernal, and a graduate student at the time, and the group of John Beacon. Actually, we put the 2 papers on the very same day on the archive. Then this was followed up by a couple of papers on kaon, on the neutrinos from kaons. And how can we search for these neutrinos with neutrino detectors? Actually, we can use the superkamikande data. The diffuse supernova neutrino background analysis lies just at those energies in the few tens of MeV. And one can set bounds on the spin-independent and spin-dependent. The bounds from spin-independent are not that competitive with direct searches. They were not already back at the time, even less now. But in the case of spin-dependent, they could be competitive bounds at the low masses, around a few GeV, coming from these neutrinos. And let me stress that these are unique limits in the case dark matter annihilates dominantly into light quarks or muons. There are no limits coming from high energy neutrinos as the ones I showed you in the previous slides. Okay, so let me move to higher energy, to higher masses. If we go to higher masses, we have a lower density, so we need to go to higher cross sections to increase the signal. But then we get into a regime where the interaction probability is very high, so that the optical depth within the sun is very large. However, and that is something important, the typical momentum transfer per collision scales inversely proportional to the mass of the dark matter. So the higher the dark matter mass, the smaller the transfer momentum. So actually, the key quantity to understand the capture process is just the mean free path divided by this transfer momentum. And it turns out that in the region that can be probed by, for instance, IceCube, we are in the region where these they are very frequent collisions, but the result is very similar to the thin regime because the momentum transfer is very, very inefficient. So actually the capture rate scales very similarly as in the case of, and this is in the standard case in the thin regime. And the limits were, there were some limits using IC22, so it's like a fourth of the actual detector now, only using 100 days. So I guess it's time to update these kind of limits. Then, so far I've been discussing only about the scattering of nucleons, but what about the scattering of electrons? Can we have capture of dark matter when scattering off electrons? And this was suggested more than 10 years ago in a paper by Kopp et al. And then the idea is that the electrons have a smaller mass, and the fact that this is so makes the thermal motion crucial in the calculation, which is not that important when we compute the capture due to interactions of nucleons. And we computed that in a paper with Garani a few years ago. And this is the capture rate as a function of the mass. The red line is the capture for electrons. The other two are spin independent and spin dependent. This is for constant cross section. This is for velocity dependent cross section or momentum dependent cross section. They are very similar. And you see here on the right, I'm showing you the effect of thermal motion. And in the case of this is the ratio with and without effect, without taking into account the thermal effects. And in the case of constant cross section, this amounts about an order of magnitude. And in the case of momentum dependent cross section, this can be up to 3 or 4 orders of magnitude effect. So this is very important for the case of capture on electrons. But in all these scenarios, and when we talk about the scattering of electrons, we can think of leptophilic scenarios. And even when we have the scattering of electrons, we will have a dark matter nucleon at loop level. So the question is, can dark matter scattering of electrons be the dominant mechanism to capture dark matter, or even the loop process of dark matter nucleon interactions can still dominate the nucleon, the capture in the sun? And this is something we are studying. I'm also studying with Raghu Garani, and here I'm just showing you, yes, for instance, in the case of a scalar mediator, still even at the loop suppressed process, still capture is dominated by interaction with nucleons. This is different from what happens with the pseudoscalar case, for which scattering with electrons can be very important. And these results are also based on a two-loop calculation that we are also preparing. And the important thing is that we can set the strong bounds on the dark matter electron scattering cross-section by measuring neutrinos, which have been produced from dark matter capture, mainly from dark matter nucleon interactions via loops. Okay, let me go to another scenario. In this workshop, we have seen also some talks that we had on Monday on self-interacting dark matter, so I won't really discuss the goodness of these scenarios, but just to say that in the case of, in the context of capture in the sun, this adds another component. So self-interaction enhances the capture rate, but most importantly, it happens that dark matter could reach equilibrium even if it wouldn't without self-interaction. So for very small dark matter nucleon cross sections, due to the existence of self-interactions in dark matter, that could produce a significant flux of neutrinos. And actually, this was a study using also an old data from IceCube for very small dark matter nucleon cross section, but large self-scattering cross section, the fluxes of neutrinos could be detected. And actually, the values of the self-scattering cross section that could be tested in this case are just in the ballpark that this alleviates problems of a small scale structure. Then we can also have secluded dark matter scenarios that we also heard in this workshop, mostly focusing on trying to detect those decays of la mediator inside the detector, so produced in the detector and detected inside the detector. Here, if the mediator is longer lived, it could happen that this dark matter, which is captured inside the sun, annihilating into this mediator, which is metastable, but travels outside of the sun and then decays into standard model particles. The main effects are that we have higher energy neutrinos, because now the decays into pions and kaons which produce higher energy neutrinos are produced outside of the sun, so we don't have any problem with energy losses. And also, if this decays happen just not outside, but just before getting out of the sun, also it's important that there is will be less absorption for high energy neutrinos, also producing a higher flux. And actually, this has been studied in different papers, and the main outcome is that we can set bounds a couple of orders of magnitude more stringent than what we have with in the standardized scenario. Also, there is only an analysis using IceCube data, but all IceCube data. So let me move now to the dark matter annihilations or decays in halos. So where should we look? This is similar, the usual suspects here. So we have the galactic center, dwarf galaxies, galaxy clusters, the extragalactic background. So you all know that dark matter annihilations or decays are composed of two parts. So we have the galactic component and we have the extragalactic component. In the case of decays, it depends on the linearly in the density. In the case of annihilation, it depends quadratically on the density. Also, let me stress that in the case of the extragalactic component for dark matter annihilation has this halo enhancement because the square of the average is different from the average of the square, and that introduces a factor which can be 10 to the 4, 10 to the 5, and there are uncertainties of that. But even taking all those uncertainties, it turns out that the galactic contribution for annihilations tends to be, is very likely to be larger than the extragalactic one. Okay, so let me show you the results with neutrino detectors for annihilations in the galaxy. These are the results, again, on the annihilation cross-section versus the mass. Again, at high masses, neutrino telescopes like Antares and SQ, in particular, Antares in this case, because it's situated located in the right hemisphere, in the north hemisphere, to look at the south hemisphere, which is where the galactic center is. At low masses, we have limits more stringent coming from Super Chemicande. There have been other analyses using looking for neutrinos from dwarfs or Andromeda, but they are 2 or 3 orders of magnitude weaker than what we can do with annihilations from the center of the galaxy. And there is an important difference here with respect to gamma rays, because the background here is atmospheric neutrinos in all cases. We don't have to be worried about modeling the flux of neutrinos from those objects. What about the prospects for the future? Well, similar to what happened in the case of dark matter from the sun, we have in the future, these limits could improve by 1 or 2 orders of magnitude, getting very close to the thermal value of the annihilation cross-section in the case of X-ray annihilation in the early universe. Okay, so what about decays in the galaxy? Actually, for energies below 10 TeV or so, which means masses below 10 TeV or so, there are almost no limits on the neutrino flux from dark matter decays computed by the experimental collaborations. Actually, there was in the late 80s, more than 30 years ago, there was in this paper, there was a proposed name, which I quite like, for these kind of candidates, in contrast to WIMPs. They would call it WUMPs, which is weakly unstable massive particles, but the name didn't stuck. So, but anyway, the bounds from the diffuse flux were estimated in the early 90s. Also, the first bounds considering the galactic flux were estimated in the early 90s, although using a dark matter profile which doesn't actually fit what we expect from the Milky Way. They were more carefully calculated by a paper by myself 12 years ago, and then there was a follow-up of using Super K data and prospect for IceCube data on the dark matter lifetime, typical lifetime limits going the 10 to the 25, 10 to the 26 seconds for different masses. And as I said, there is only one analysis that I know from experimental collaboration, which is using IC22, so a fourth of IceCube, but not even 1 year of data. So I think it's also time for the experimental collaborations to update the limits from decays. So what about we talk about heavy dark matter? So you all know that a few years ago, IceCube discovered the flux of high energy extraterrestrial neutrinos. And among those, there were 2 PeV neutrinos. And after those events were announced, Feldstein and collaborators posed the following question. Can the highest energy IceCube neutrinos be explained by heavy dark matter annihilations or decays? In the case of annihilations, one would need a very high annihilation cross-section that get into problems with a unitarity limit. But in the case of decays, this is not a problem. We can have a lifetime with 10 to the 28 for a PeV dark matter and produce the right rate that was observed by IceCube. And soon after the Feldstein paper, there was a paper by Smiley and Serpic, who actually considered the possibility to explain the entire spectrum observed by IceCube. This has got some interest in the community, and there have been many analyses following the first ones, and many production mechanisms have been proposed to explain how to produce this very heavy dark matter in the early universe. And just an example, I'll show you this analysis I did with some collaborators on the 6-year HESI data. HESI is high energy starting events, contained events in the IceCube data. We consider astrophysical flux and dark matter flux. We did the bands for annihilations and decays, but let me concentrate on decays. This is the lifetime limit, the lifetime versus the mass. The color line is the limit. Everything below the line is excluded from IceCube data. And the dotted line here are limits coming from gamma ray, which are also producing these decays. And as you see, when dark matter decays into BB bar, the gamma ray limits are better. But when dark matter decays, for instance, in tau leptons, the dark matter limits with neutrinos are better. So this is the take-home message, which is neutrino limits are better than gamma ray ones for relatively hard channel for masses of 100 TeV or so. There is a preliminary analysis using the recently released 7.5 years of IceCube, which is very similar to what you get with 6 years. And there was a very nice compilation of all these annihilation into a pair of neutrinos. These were mentioned by Miguel in the previous talk, and this paper covered a huge range of energies. And the idea behind why considering dark matter annihilations into neutrinos or decays into a pair of neutrinos was suggested by John Beacon and collaborators more than 10 years ago. And it's very simple. It's that given that neutrinos are the least detectable particles in the standard model, considering dark matter annihilations or decays into a pair of neutrinos is the most conservative scenario. And this was followed up by a couple of papers by myself. And actually, this region is particularly relevant for this channel and actually for this workshop because this is sub-GeV dark matter. But we can turn just 90 degrees in the Feynman diagram, then we have interactions with dark matter. And we can search for features on the spectra. We can search for features on the energy spectra, on the arrival directions, on the flavor composition, or on the time of arrival compared to other messengers. And there are basically two types of effects. We have incoherent or coherent effects. Incoherent effects are absorptive effects, so we search for an absorption of the flux of neutrinos from astrophysical sources above some energy, or at some energy we have some resonant effect. Like for instance, one can search for dips in the supernova neutrino spectra, which is something I did with Jasam Farsan with Super K. One can search for full absorption of supernova neutrinos, energy dependent anisotropy of high energy neutrinos by looking at regions, comparing regions where neutrinos would go through a huge amount of dark matter comparing to others that would cross smaller amounts of dark matter. One can also search for the full absorption of high energy neutrinos from point sources, knowing that those neutrinos coming from that source, just the fact that we have detected that neutrino sets amounts on the scattering cross section. And one can also set limits from time delays of high energy neutrinos compared to other messengers like gamma rays. Then there is a way to search for these effects when there is a resonance. This is what we call redshift integrated resonance. And this is an unpublished paper that I have written with Tom Weiler for more than almost 15 years. We'll see if we ever publish this, but it's very simple. So this is a graphical way to see if a particular model produces a dip, an observable dip in the experiment. So this is the dark matter, the ratio of the dark matter mass over the mediator mass and versus the mediator mass. You have your model, you place your parameter region here. You see the black lines here. These are the coupling. So if the region of the parameter space is just to the left of the black line for which are given coupling, then that model would produce very likely an observable dip. So, and then we have coherent effects, and with this I will get close to finishing.
Sergio.
Yeah. Tell me. Nicolas?
I think you have like yes, can you hear me?
I can.
You have like 1 minute more.
Yeah, I'm almost finished. So we have coherent effect, which just induce like a matter effect, like the usual matter effects in neutrinos, and there are many different ways to search for this. For instance, neutrinos could couple to ultralight dark matter and produce a third flavor ratio. This is also a paper I wrote with Jasam Farsan a few years ago, or suppressing neutrino production in the early universe. Or actually, one can even induce time variations or distortions if this very light ultralight dark matter is very, very light, and that can be searched for detectors like Juno or Dune, etc. And well, I have also cosmological and astrophysical effects like damping of the matter power spectrum, and that can be searched for with Milky Way satellite counting or Lyman alpha forest. I will not get into details because I'm running out of time. One can put all this together, and this is what we did in this paper. And then there was also a paper that I think has been mentioned by Miguel in the previous talk. So let me just conclude. And there are many potential neutrino dark matter connections, many indirect dark matter signatures with neutrinos. Not all of them have been covered in this talk, but some are unique, like the dark matter in the sun. And neutrino detectors are complementary to direct searches, to indirect searches with other messengers, and to astro and cosmological observables. And with this, I'm done. Thank you.
Thank you very much, Sergio, for this very complete talk. Are there urgent questions or comments for Sergio? Well, I can ask one. So I think you mentioned twice the dark matter self-interactions, but I think it was in slide 10 or something like this. If you could go back.
So say it again, dark matter interactions?
Self-interactions. I think it was on your
self-interactions.
slide 10. So I think
Okay.
I missed the point, or 11.
This one?
Yes. No, before. I think just before that. One before, no? Exactly there.
These are not self-interaction. These are strongly interaction.
Ah, okay.
This is just
That's why I was confused.
This is dark matter nucleons, but the strong interaction on heavy masses.
Mm-hmm. Yeah.
So this,
Okay.
look at the
I
masses.
was thinking dark matter self-interaction, so that's why I was kind of confused.
Self-interactions is here.
Yeah, but that I understand. Okay. Thanks. Yeah. Any further questions or comments?
May I have a quick one?
Sure.
So Sergio, regarding the sub-GeV window, how I remember some papers last year about whether the bounds already were touching the thermal cross-section, and I would like to know from you whether that can happen with current data, or whether that will happen with future data. I don't know.
That will happen with future data.
So, okay. Because there I cannot see the projections in the future, for example.
No, here there are no projections. This is a current status.
Okay.
So this is what I mean, that this will happen with future.
Okay. Thank you.
Good. We are kind of running late, so let's thank Sergio again. If you have more comments or questions for him, we can ask him during the discussion. So thanks a lot, Sergio. And now we have the coffee break, so we can reconvene in